Okay, so its lift and its passengers of total mass 800 kilograms is raised from the bottom to the top floor by means of a cable attached to its top. As it gets closer to the top floor, the lift begins to slow down. Given that the tension in the cable is 7,440 newtons when the lift is slowing down, determine the deceleration of the lift. Okay, so we're given the tension, 7,440 in that cable. We also can work out the weight of the lift. So it says the total mass, so we've got a combination here of the lift and the passengers is 800 kilograms, so mass times gravity, so 800 g. So if I work that out now, that's 800 times 9.8. If I do that on my calculator, I get 7,840, okay, newtons. Now, what's interesting, I'm sure you know if you think about the process here and the situation of this question, is that lift is started at the bottom, didn't it, and it's going up to the top floor, okay, and we are meeting the sort of situation towards the end of its journey, because it says as it starts to slow down. And of course, if you think about a lift, when it starts at the bottom, it'll speed up, it'll accelerate, it'll lift upwards then, and perhaps travel at a sort of steady speed for quite a while. But when it gets closer to its destination, it's got to start slowing down, isn't it? Okay, that's why it says here, it's got to start slowing down so that it can stop comfortably at the floor, in this case at the top floor. So what in that situation, when it starts to slow down, what you find is that the weight, okay, is actually greater than the tension in this lift, even though it is still going upwards, okay. And it's important to have my direction of acceleration going in the direction that the lift is traveling in. So the lift is still moving upwards, however, the tension in that cable is not as much as the weight. So, you know, if you were sort of like looking at this without reading the context above, you'd perhaps think that the lift is actually going down. If you hadn't read the information at the top, you'd think, well, that is greater, that's a greater force, so it's moving downwards. But that isn't always the case, okay? So we've got to see the context, and it is rising, but the fact is it is slowing down. Okay, and in order for it to slow down, what happens is that the tension in that cable is not as much as it was earlier in the journey when it was lifting it, when it was increasing its speed. It's now it wants to sort of slow it down, so it sort of slacks a little bit, and then that weight is greater than that tension, and it will slow down as a result. But hey, if we apply Newton's second law, okay, in the direction of increasing motion, and that's important that we consider that in the direction of increasing motion. Well, we know that the resultant force is equal to mass times acceleration. So because we're going upwards, this is the leading force, okay, even though it's less than this, it is the driving force of this lift, 7,440, and then we take away what's resisting it, which is this weight, 7,840, okay, and then we put that equal to then of course the mass, which is 800, and then the acceleration, which we want to work out. So if you work that out, you end up of course having there smaller number take away bigger number, you end up with a negative, and it's negative 400 equals 800a, and then you know if we divide by 800, we then get a, okay, so that would give us a to be negative. A is negative 0.5 meters per second squared. And that's just telling us what the fact is now, it's explaining that it's decelerating. Okay? So when you get A as a negative, it's declaring that it's slowing down, it's a deceleration. And they say determine the deceleration. Well, we need to look at the size of that now and say, well, yeah, the deceleration is 0.5 meters per second squared. If you're declaring what the deceleration is, you don't have to put a minus in there then, okay? Because the fact that you use the word deceleration is actually showing that the acceleration is negative, okay?